Okay, so everyone knows my prior equation, but this is a little bit different. And it states basically that you can go to any area in the universe that is equivalent to itself in a spectrum of a wavelength. So what I'm going to show you, if I can find my pen one more time. I thought I had it on me. Okay, what I'm going to show you is this second equation right here. Now, I started off with a mass, and it doesn't necessarily need to be magnetic, but it could be if it wants to. And I turn time dilation after that plus space-time paradox. Okay? Then I subtracted force times, congruent to acceleration. And then I put times 5 plus area times time to the third, and the rest I left off. It would stop right about here. It stops right there. My pen's running out of ink again. But then I go to the golden constant that I made up, and I add motion to it and subtract the light. The reason why I'm subtracting the light is because the light is around the tunnel that happens to be where you are, so you can travel through time faster than normal or even past light speed or around light speed or whatever speed you're going before you go in there is multiplied by the force and acceleration. And then by phi. Now, then after that I put space and time, and I congruentize it to time squared, and I congruentize that to wavelength. It says 1, 2, 3, 4, 5, 6. And I have 1, 2, 3, 4, 5, 6, 7, 8. So the last thing I'm going to do, or I guess times squared is 2, so that could be 7. T dot is my original way of writing it. I'm not sure how many people write times squared or think it's easier or funner to write times squared, because I figured out time to the third and it's down here. Where did I put it? Or it's over here, sorry. Time to the third right here. And I made it with another one after that, which is space-time and wavelength. I think it needs to end in wavelength. And I think that when you square or put a number to the third, you wind up finding out that it's similar to each part, but in different dimension, right? So naturally we think that, but time squared showed up in the third dimension. Time to the third ended up in the fourth dimension. So I'm not sure how you guys want to word this or put that in some other order, but I put time to I did put time to the third right here. Okay. So time to the third right here, an area phi, force congruent to acceleration, space-time paradox, time dilation, and mass, over, not in that order obviously, but over Golden constant plus motion minus light times time and space, or space-time, congruent to time squared, which would be congruent to a wavelength. And how I'm going to do this is go like this and go like this. Now if I do that, this is already in parentheses. This counts for itself in both this one and this one. And in this one and in this one. So from beginning of the parentheses of this to here, then from this to here, we get an answer. What I wanted to tell you guys about what I did about this, besides the first time I did it, was that I found out that to keep a wormhole open, you need to have it be 9 dimensions. So let's start by saying that this right here is the mass, and we'll even make it oblong or saucer or anything. And after we do that, we do time dilation, which is this design that goes down here and forces itself off of magnetism and goes around, comes up, and matches up with another magnet right here. Then it would wind up passing through a magnetic hole right here that is squared. So I figured that this is time dilation. How I figured out that this is time dilation is because on my computer that I'm using right now, I found a number that was, if you squared it after a square root and put a number before it, such as pi, you get 0 is 0, -1 is 0, and 1 is 0. So I wrote that down. I'm pretty sure they can make me look that up again if I want to, but I think I wrote it down. And I found out that that's the part that we had to fix, because as you can see, I have a number of lines that go from everywhere to somewhere else, to somewhere else, somewhere else, somewhere else, somewhere else, on both sides of the paper. Now, continuum paradox is basically this egg. It's basically an egg-shaped thing that has this wrapped around it, and then this going above it. If not above it, it's in a circle, and it just wraps itself around it somehow. So that's how I got my space-time paradox. Then, so if we add that to it, we're going from the time period that we're at to the space-time paradox. This is dimensionally. So, like I'm saying, a wormhole works dimensionally too. So I don't see what the big deal is about why I couldn't put this in draconian form. after quantum form, and then after that plebeian form. But so we got that part down basically. Force minus force time acceleration gives you a static frequency, and we'll label this the bottom part of the space-time situation. All right, now and then we go to phi. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now that was either underneath. I don't know if that's either underneath or it crosses it out. And plus area. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and there's a ball right here. There's a ball right where I said that was. And time to the third. Time to the third starts off with time or dimension 4, like this. How I figured it out, I use a computer, I use a Desmos calculator, and then I figured the rest out because it wouldn't tell me what it was. And then so after that you go and make a circle for an orbiting body to enter through, or not an orbiting body, but a massive body to enter through. And then you have this erasable but containable thing that happens the whole time. Now, if I were to do anything after that, I'll put inertia there. Inertia is right here, and we'll go right there, and we'll stop, go right here, go right there, and keep going, keep going, keep going. Now, if I put inertia there, I'm putting a golden constant after it, or the reverse of a golden constant, because I'm dividing it by itself, or dividing it by the golden constant. So before this, we're going to go ahead and put this here, divided by a golden constant. One, 2, 3, 4. It matches up at the inertable point. So here we go. I'm going to add. I'm going to scratch this off. And we're going to add Z. Not the plane Z. It's not the plane Z. It's inertia. I've already made it up. I don't know if they wanted me to make that up for them, but so I've already made up inertia, and I don't know why it's fuzzy now, but I felt like I just got my camera taking a picture of me or something, and now I'm gonna be a wanted citizen or something. I don't understand that. Z, and then the golden constant plus motion. Plus motion, so 1, 2, 3, 4, 5. And it leads back to the magnetic center of whatever is underneath space and time. Okay? Then we subtract light. And there'd be no need to do this because, well, you already are in space and time. But we're doing it anyway. And you're traveling along wavelengths. And we'll just imagine that there's a massive planet right here. Okay, let's see what happens with the massive planet right there. light minus light. See? It does make an Einstein-Rosenberg bridge at the same time as making a wormhole, but let's just see if it's an Einstein-Rosenberg bridge and not a wormhole. So we subtracted light, got to the top of a mass, and we orbited it in its relative position. Okay, you see that? We orbit it in its relative position. After that, what you see is that you need to use space and time. So it's 1, 2, 3, 4, 5, 6, 7, 8. And it becomes this kind of confusing thing around a mass because of relativity. Now time squared. I'm just showing you the whole thing of time squared right now because a lot of people say that you just put it at the bottom of whatever you're doing, and it's not the truth. I made this up because I understood what it was. And as you can see right here, it goes all the way to the other side, and you guys would have been wrong. Okay. Now we're going back to the bottom of where where the bottom of the wormhole is. 1, 2, and it's time squared. And we use a wavelength. So we're using a wavelength, 1. And it shoots straight out because it's negative force. And after here, it would break a plane like of area, like glass. And it would keep going up and go around here, come down to the spatial paradox, space-time paradox, go around in a circle over here, come back, and it goes around and makes a point of the space-time paradox. And what's supposed to happen is there's supposed to be more like a grid to the space-time paradox. As you can see, I saw it coming. But it makes a grid to the space-time paradox. And then you go back outward and inward and inward and outward. And your mass is a little bit further away. There's a saucer. Or this is a body of mass that's like Earth or something. But it's going in reverse time. Now, since I put z at the top of that, I have to add one more equation to the bottom half of this. And what I would do is maybe put k. K, 1, 2, 3, 4, 5, 6, 7. And K works the best. If it's not K, I'm running out of time on this computer, and I'll do it again for you guys in a minute. So I'll load. I just gotta not load, but first of all, stop shaking. And second of all, I hope you guys got a lot of time on your hands to watch this video because it was an interesting video to show you guys due to the process of time squared and space-time paradox and everything else that was going on inside my math with the golden constant. And even in interval or in an unmagnetized mass. So I'll see what you guys say about what my video says, and I'll like to hear back from you guys. This does not count yet. Not yet. Okay, you had wavelength and golden constant. So, alright, and then that's, well, if that's that, then I would also probably put up in there time displacement. If I put time displacement in there, it might look a little bit. I'll do one more thing. Here's time displacement if it were it. Not only this, but this is going to be very interesting to you guys. This is an Einstein-Rosenberg bridge then. There. There. Instead, we'll put time displacement. All right, everybody. All right. This has been fun talking. Guys, enjoy the fro. Look at the fro. I mean it. I'm all about it. All right. Talk to you guys later.